Okay, I'd like to talk about some of the common mistakes that were made on the first test. So in the first problem, a 20-pound box was moving down a curved track, and as soon as you see a particle moving on a curved path, you know that it has acceleration back toward the center of curvature. So most people identified correctly that there was a normal direction perpendicular to the path. There was a path force, which was perpendicular to the path. Many people had the tangential direction going up, but the package is moving down, so the tangential direction should be going down. One error that showed up a lot was people realized that the particle is moving and indeed accelerating down the path, so they felt compelled to put a force in the tangential direction. The reason that the package accelerates down the slope is because there's a component of the gravity force in the tangential direction. So just because something has acceleration in the tangential direction doesn't mean you've got to put an explicit force in there. As long as there's a component of some force acting in the tangential direction, that will accelerate the package down the incline. So no force there. So that was one problem that came up a number of times. Another common problem was the fact that because the package can't go through the path, I suppose, people simply said some of the forces in the normal direction equals zero. So that's a big error because, again, anything on a curved path is going to have acceleration toward the center of curvature of that path. So many people, I think most people correctly applied the equation. Some of the force is normal as mv squared over rho, where you find rho from the path equation. Often when people did the normal force summation properly and solved for the path force, they then did not go on to say some of the forces tangential is equal to mv dot. People tried to manipulate the path equation to find a magnitude of the acceleration based on x dot and y dot. All that was required was to simply sum forces in the tangential direction. If you're applying Newton's laws in n and t, write Newton's laws as completely as possible in both the n and the t directions. It gets you part marks, and it also lets you step back, look at what you've written, and see if you can see a path toward the solution. The angle between the path force and the vertical, that should be tan minus 1 of the slope, so tan minus 1 of 0.4. By fluke, you can do tan minus 1 of 10 over 50. Strictly speaking, that wouldn't normally give you the angle of the tangential direction. A lot of people fluked into that, and I didn't take off any marks. Now in the final part of the question, where you're trying to find the angular velocity of a line from O to A, the key is to resolve the velocity vector 30 magnitude along the along the transverse direction, and that magnitude is going to be r theta dot. Most people found r correctly. A mistake that was often made was, okay, the velocity vector is r dot times the ur vector plus r theta dot times the u theta vector. I saw a lot of v equals r dot plus r theta dot. Okay, you want to be very careful not to do that. You cannot simply add the scalar component magnitudes and get the scalar magnitude of the whole vector. Okay, so respect scalars versus vectors and keep yourself out of trouble. A final error that was fairly common, people were trying to get a relation between r and theta, and they looked at this right triangle and they said r is equal to 50 secant theta. That's true now, but it's not going to be true as soon as the package starts to move. So you cannot take this as a generally true relation between r and theta and then differentiate it to solve part C. This only applies if the 50 is a constant. So if you go back and look at some problems where we were able to express the path equation as something secant theta, you'll see that the something was a constant. Okay, for the second problem, you're in a simulator. there's scenery going by you on a screen, and your chair is held in a static 10-degree backward tilt. You feel a force N2, which is simply mg sine 10 degrees, and the acceleration you perceive is the force you think is pushing you forward divided by your mass. So it would not be correct to use the mass of the plane in trying to figure out the perceived acceleration. I think the most common mistake in problem 2 was people saying that the sum of the forces that way was equal to some sort of ma, and the sum of the forces in the n1 direction was equal to 0. Okay, so you are sitting in a chair. We are going to solve for the static forces on your back that make it feel like you're accelerating. Okay, so once we know how fast you feel you're accelerating, now we're going to imagine that you're inside an airplane taxiing down the runway horizontally. So if you think you're accelerating with acceleration A, then if the engine of the plane was thrusting the plane forward with a force F, then that F would be total mass times the acceleration that you perceive. Because you're in the flight simulator at 10-degree static tilt, but you're simulating a plane that's rolling horizontally down the runway.